Hello. One network sounds very unique in a area of time when everybody is building more and more things, and we were not an exception. As a Google, we were latecomers to the cloud computing game, and with that, our team started building and building and building, and within a few years, by 2020, we organically grown to more than 300 products with a lot of infrastructure, with the multiple network paths. And our customer noticed that the products were not integrated, and we noticed that our developer velocity is actually low because every time we need to release new feature, we need to release it in n times on every network path on a different infrastructure. And the most scary part and important part was the policy. Policy is something that cloud providers worried about day and night because all the cloud infrastructure is controlled by policy. So how do you make sure that policies are being controlled on every path without any exception, without needing to modify these 300 products? And so let's look why networking is complicated. On the left, you see Google Prod Network, and Google has actually its own network, as you know, and we're running search, YouTube, etc. And on that, we build some cloud products. For example, here, Borg is a container orchestration system. On it, we build Cloud Run. On the top of Cloud Run, there is its own networking. Then there's a virtual networking on GCP itself, which is called Andromeda. And on top of it, we build different runtimes like a Kubernetes GKE and GCE, which is a compute engine with the VMs, right? And over there's, again, networking its own. And the GKE, as you know, Kubernetes has its own layer of networking. On the top of it, there are service meshes, and then the same thing applies on multi-cloud or the customer premises or distributed cloud, where layers and layers happen. And then what happened, we actually, in each environment, we build applications. And these applications, again, they run on different runtime, they have different properties. And this combination of infrastructure on different network path and different runtime created an n-square problem of what I usually call switches, right? Something works here, something doesn't work there. And so what's the solution? The solution, what we called One Network. It's a unified service networking overlay. And what is the goal of One Network? We say we want to define policy uniformly across services with the constraints of what I just explained, that it heterogeneous compute, heterogeneous networking, different language runtimes, coexistence of monolith services and microservices, and it's all across different environments, including multi-cloud, other clouds, public and private clouds. And so the solution is a One Network, which is like frustration. You can think about, why do I need so many networks? Can I have please one network? So One Network it is, policy managed at network level. We iterate towards One Network because it's such a huge architectural change to manage costs and risks, and it's very much open source focused. So all the innovation went into open source, and some went to Google Cloud itself. And so how to explain One Network? We'll build on one proxy. Before that, every team and basically a lot of proxy were floating around. One control plane to manage these proxies. One load balancer that is wrapped around the proxy to manage all runtimes, so both GKE, GCE, Borg, managed services, multi-cloud, etc. Data plane APIs to extend the ecosystem, they're universal, so we can extend with both first-party and third-party services, uniform policies, and again, it's across all environments. When I presented this particular slide in 2020, everybody said it just sounds too good to be true. And it was at the time. So who is going to benefit from one network? Everybody, actually. So these are the folks the roles that we will put together who benefit from one network. They vary from people who care about security policy to DevOps and networking who care about network policy, to SREs who care about provisioning large number of microservices or services, and to application developers who actually want to worry about their own policy without needing to interact with the platform admins or platform engineering folks. So there's the width, the depth, and the isolation at the same time, so it's a partition. As well as universal, right? Everybody cares about orchestration of large environments, and everybody cares about observability. So what are the principles? We build one network. We build on 5 principles. We're going to build on common foundation. Everything is a service. We will unify all paths and support all environments. And then we create this open ecosystem of what we call service extensions, which are basically pluggable policies. And we then apply and enforce these policies on all paths uniformly. Let's start with the first one. This is one network pyramid I put together because I was thinking how to explain the narrowing scope of any layers, right? So we start with the common purpose Envoy proxy, and we'll talk more about it. And it's available, it's open source proxy available both on GCP or on-prem anywhere. And then we wrap it around and build around it GCP-based load balancers, which actually work both for the VM containers, serverless, etc. And then we build on top of it, you can build on top of it controller, and now GKE controller, and now you have GKE gateway that uses the same underlying infrastructure, but now only serves GKE services and workloads, and it understands behavior of GKE deployments, right? And the top of the pyramid is where you actually don't see gateway at all because it's fully integrated into Vertex AI, which is our AI platform, for example, and it's just implementation detail. And so all of that is using the same infrastructure across the product and across the paths. And so all of this layer are controlled by a single control plane, which we call traffic director. It has a formal API and everything. When I say single, it actually doesn't mean a single deployment. It means it's the same control plane that could be run regionally or globally, or could be specialized per product if there is a need for isolation. But it's the same binary that runs all over, and so you can control it and orchestrate it the same way. Now, this is one network architecture North Star, and I want to walk you a little bit from the left to the right. You can see different environments. It starts from a mobile, going to the edge, then to the cloud data center, then on to the multi-cloud or on-prem. And there are 3 common building blocks. There is a control plane, traffic director, that controls all of these deployments. There is an open source APIs between the traffic director and the data planes that call XDS APIs. And then there are data planes, and data planes are all open source, right? They're open source based. They're either Envoy or the gRPC, both of which are open source projects. And so having this open source data plane allows us to extend both to multi-cloud, onto mobile, and basically anywhere outside of GCP, but because it's no longer proprietary. And so talking a little bit about Envoy Proxy, it came out in 2016, and we really like it. And the reason we like it, and because it was great, new, modern proxy with the all advanced routing, observability as a first class, and it got immediate adoption. At Google, we heavily invested. But the reason we like it, it's not because it's great proxy, but because it is actually because it's platform with these amazing APIs, and it has 3 sets of APIs. It has, again, configuration APIs between the control plane and the data plane in the proxy itself that configures its eventually consistent APIs. And they provide both management plane and control plane functionality. There are data plane generic APIs. There is an external auth that does allow and deny, and so you can easily plug in any auth-related systems. There is a API that called external proc. So basically, you can plug in anything, and it can modify behind it. You can modify the body, and then return it back. So it's very powerful. And then there is WebAssembly binary APIs for the proxy WASM. That we'll talk a little later. There are also specific API. Envoy had right away RLS, which is rate limiting service, which is interesting to see that it could have been achieved via, let's say, external auth, which is more generic because it's also allow and deny, but yet over here it was specialized. And we're seeing that in the future we're going to have more this specialized API. For example, we're thinking of LLM firewall API. When you think that incoming traffic, you can classify it as AI traffic. You can apply rules that are specific to AI traffic. For example, you can do safety check, you can do block lists, you can do DLP, etc. So the data plane itself has also filters. The Envoy proxy has filters, both L4, which is TCP, and L7 HTTP filters. And so there are two types of them. One of them is linked to Envoy, and that changes ownership, right? If as a cloud provider we link, then it means it could be only our filters. And if customer runs it on its own, then it's theirs, and we cannot mix and match. And the WebAssembly filters, it's a runtime that you can actually have both first-party and third-party code loaded into the data plane. And Google heavily invests into open source proxy WASM project, and actually we released a product just right now. And so you can think about these filters could be changed. They could be either request-based, response-based, or request-response, depending on how you need to process it. All of that is configured by Traffic Director. So talking about Traffic Director, it's XDS server. And what it does, it combines 2 things. It combines very quickly changing dynamic configuration, for example, the weights and the health, with the static configuration as how you provision a particular networking equipment. And that magic we put behind Traffic Director, we call it GSLB, the Google Global Service Load Balancer. It's a global optimized control plane that it's the same algorithm that Google uses to send traffic for search, YouTube, Gmail, anything you do with Google uses this load balancer behind it. And what it does, it optimizes, globally optimizes RTTs and the capacity of the backend. And so it finds the best path and the best weight to send to. And it also has a centralized health checking, so you don't need to do N-square health checking from the data plane. Because one time we actually noticed that if you do N-square health checking, you're going to end up with the 80% of throughput through the data center being just health check only. right? Leaving only 20% for actual traffic. So removing that 80% overhead is great. And also it's integrated with auto-scaling. So when there is traffic burst occurs, you don't scale up step by step. You can just scale up in a single step because you know how much traffic is coming. And in the meantime, traffic is being redirected to the closest. So traffic director handles here policy orchestration because when administrator creates policy, it delivers it to traffic director, and then the traffic director provisions all the data plane with this policy where they enforced. And the second principle is everything is a service. And so this is actually a diagram of a real service. It's cloud service, internal. And now think about how do you manage such a service, right? There are different colors, they mean something. There are different boxes, they mean something. The lines are all over. And how do you reason about such an application? Is it how do you apply governance? How do you orchestrate policy across this? And how do you manage these small independent services, or how do you group them in the different groups? So One Network helps here. Every of these microservices is imagined as a service endpoint, and it enables this policy able to orchestrate and group these service endpoints and orchestrate over them without actually touching services themselves. So everything is done on a network. So there are three types of service endpoint. There's a classic service endpoint of customer workload, where you take a load balancer, you put it in front, you got a service endpoint, and you hide, for example, shopping cart service in two different regions behind it. That's typically how service is being materialized. The second is a newer one, where there is a relationship between a producer and consumer. For example, you have a SaaS provider who builds a SaaS on GCP and then expose it to the consumer via a single service endpoint that is materialized via this product that Google Cloud has called Private Service Connect, right? And so there is a separation of ownership, and the producer doesn't have to expose their architecture out to the consumer. And so consumer doesn't know about all the stuff that is producer running. The only thing they see is a service that is endpoint, and they can operate it. In this case, you can think about the producer being a third party that is outside of your company, or even your shared service. If you have a shared service within your company and you want multiple teams to use it, this is type of architecture you want to do, because you want to separate your own implementation from a consumption, and then allow every customer or consumer to put their policy on a service endpoint. And you can expose a service endpoint per consumer, or expose a single service, or as many as you want. There's also headless services. These are typically defined by service meshes, where they're like within a single trust domain. And in this case, services are just materialized as an abstractions, because there is no gateway here, there's no load balancer, and each of them is just a bunch of IP ports or of the backends. Now, example of this is AI, obviously. So we're looking at a model as a service endpoint. Over here, the producers are model creators, right? And the consumers are Gen AI application developers. And so you can see how everything that producer, for example, the inference stack is hidden behind a private service connect, so nobody even knows what is they doing there. And then the application, different application connect to this particular service endpoint. The third one is to unify path and environment. Why would we want to do that? Is to apply uniform policies across services. And to unify paths, we first have to identify paths. So you can see here 8 paths that we identified. This is a generalization. Actually, there are lots more, but we generalize them to 8. And then for each of them, we identify a network infrastructure that have to implement the path to apply the policy. And you can see there's both external load balancer for internet traffic, internal load balancer for internal traffic, service meshes, egress proxies, even mobile. And let's start looking at one at a time. So GKE, gateway, and load balancer, they typically, that's how services are materialized. And so what we did, we involve Sidecar Envoy, which was original deployment, to become a managed load balancer. And we spent about more than a year of hardening it in open source to become available for internet traffic. We also have global and regional deployment. Then global deployments are used for customers who have global audience or who actually care for cross-regional capacity reuse, or in general, they need to move around. Versus regional deployments for customers who care about data residency, especially data in transit, or looking at the regionalization as an isolation and reliability deployment. So we provide both, and it's all connected to all runtimes. So the second deployment here is a service mesh. You probably heard about Istio, which is probably now the most used service mesh. And the most interesting part about them is that they very clearly define what is service-to-service communication needs. And it needs service discovery, it needs traffic management, it needs security, it needs observability. And once you separate this into these independent areas, it's easy to plug each of them independently. So for Google product, we have Cloud Service Mesh, which is Istio based, but it's backed by Traffic Director and also by Gateway APIs, as well as Istio APIs, and it works for VMs, containers, serverless, etc. So that is out. And then Google had Service Mesh more than 20 years ago, since forever. And that service, before service meshes were a thing. And the difference between Google Service Mesh and the Istio or any other service meshes, that we had it proxyless. So we had a proprietary protocol called Stubby, and we had a control plane that goes to Stubby, and we provisioned Stubby with the configuration and everything, and it basically was a service mesh the same way as you see it now. And so we exposed this proxyless service mesh notion to our customers and to open source, where gRPC used the same APIs to the control plane as Envoy. And obviously that allows to reduce consumption because you have extra proxy, and it also it's basically super flat without having any maintenance, right? Because you don't need to install proxy, there is no lifecycle management, there is no overhead here. And similar, but a little bit different deployment architecture is GKE Data Plane v2, which is based on Cilium and eBPF in a kernel. And so it simplifies GKE deployment networking by scalability is improved because there is no sidecar. Security is always on, and built-in observability. And for L7 features, it basically automatically redirects it to L7 load balancer in the middle. Now, mobile, actually we didn't productize. This is a concept, but we ran it for a couple years, and it's very interesting. So this extends one network all the way to mobile, and it brings very interesting behaviors, because phones, as opposed to the workloads or computers, etc., cannot actually have persistent connection to the control plane due to power consumption. And so the handshake is a little bit different, and also that would require a traffic director to build a cache to be able to support. We tried on 100 million devices or simulation of devices, and so that actually worked very nicely. And it uses Envoy Mobile. There is an additional, this is evolution of Envoy proxy that is typically used to Envoy Mobile, which is a library that is being linked into the mobile application. And one of the interesting use cases here is if you have 100 million devices and one of them goes rogue, or you need to figure out, having a control plane would allow you to identify that particular one, deliver a configuration to that particular one, and get the observability of whatever you need, or shut down that particular one. So the value is there. Now, the second project that is also a work in progress is a control plane federation. Now you can think about multi-cloud or the on-premises, where a customer outside of GCP is running pretty much similar deployment, but it's not GCP managed. Now you're running your own Envoy, or you're running your own gRPC proxyless mesh with a local Istio control plane. And so in this architecture, we are using local Istio control plane to do this dynamic configuration, like to make sure that the health of the backends is being propagated. So if the connection between traffic director and the local XDS control plane breaks, then the deployment on-prem or the cloud can function just fine until they reconnect. But then you still have a single pane of glass, and you can manage multiple numbers of these on-prem or multi-cloud deployments or point of sale deployments. You can imagine those can go into the thousands from a single place. So bringing it all together, this is what it looks like. We already looked at this picture. So you have all the load balancers and the mesh, and they go across environment, including mobile and multi-cloud. And so that was a backbone, right? Now, how do we use the backbone to enable policy-driven architecture? We introduced the notion of service extension. And for each APIs that we discussed before, whether it's external OSD to allow and deny, whether it's external processor, at every point there is a possibility of plugging these things, policies in. And the examples here are, for example, a customer wants to have its own OTZ. They don't like OTZ that we provide to them, so they'll be able to plug in. Or another example is Apogee, which is our product for API management. Having service extensions changes paradigm of how API management is actually done, because previously you would need an API gateway, a dedicated API gateway to do API management. Over here, API management becomes ambient. It's going to be available because one network is so big and you can plug at any point, and the same API management will be available at any point, whether it's on edge, service-to-service communication, on egress, on mesh, etc. So you have this change from a point solution to the ambient presence of the policies or the value services. Another example is here is a third-party WAF. We have our own WAF, but our competitors can bring their own WAF, and it's open ecosystem, and the customer may be able to pick and choose which WAF to use on the same infrastructure. So they don't have to plug additional things in and then try to tie it together. It's all available. Now, the one network architecture, right, is all there. So before we discussed how it looks at one point, and now you can see how you can plug this at any point everywhere, right? Whether it's routing policies, whether it's security services, whether it's API management or traffic services. Now, how does it work actually? So we have 3 types of service extensions. One of them is service plugins, WASM-based, and it just went public preview, I think last week. And then there is a call out. That is serverless essentially. So you give the code and we run it for you. And typically people like to have it at the edge where you can immediately do header manipulation and other small functions. Then you have service callouts, which are essentially SaaSes that are being plugged in. And over here, there's no restriction on size, ownership, etc. And it's just a callout to a service. And then what we call PDP proxy, it is an architecture that allows plug multiple policies behind a proxy for the caching, and not just for the caching, and then you can do manipulation of this policy and that policy, then do this. Otherwise, so it's like operating on multiple policies. Each of these policies are represented as a service too, and they're managed by UpHub, which is our services directory. And going into the future, we're looking into the managing all of these through the marketplace and have life cycle management, because there's going to be a lot of them, and the question is going to be how one is going to pick this WAF versus that WAF, right? You need to have recommendation system, you need to worry about which one to choose. And the last, but not the least, is how do you apply and enforce uniform services? We actually came up with a notion of 4 types of orchestration policies. One of them is creation of segmentation. So if you have a flat network and you want to segment it, you can segment it by exposing one service and not publishing others. And that causes traffic to go through a choke point. And over there, you can apply policies. And it's easy to do because everything is a service, right? So now it's easy to manipulate which services are visible, which services are not visible. The second one is to apply a policy to all paths. What actually happened that every application has multiple paths leading to it. For example, it's very common deployment to have internet traffic and internal traffic going to the same service, to the same endpoint. And so when something happens, how do you quickly apply policy to all paths because you're protecting this application behind it, the workload behind it, versus worrying about, did I cover all paths or not? So you should give away that knowledge to the programmatic system that can go and orchestrate over the paths. The third one is to apply policy across an application. One application defines a perimeter, a boundary in which all these services and workload reside. Typically a business boundary, for example, e-commerce application, right, contains a front end, a middle tier, a database, and then a different application contains catalog and other things, and then the one application can call into the service of another application. So within a given application, a security administrator can say, okay, on the boundary, there are these policies. For example, nobody but this service can talk to the internet, right? And everything inside of the application cannot talk to the internet. That means the policy need to be applied to each of the workload, for example, not to have a public IPs or to not to allow egress traffic. And the fourth one is to deliver policy at the service level. So that is a management at scale. Imagine that you need to provision every VM with a firewall or some configuration, and with that you have 1,000 of them. Instead, you can group this VM into a single service, set up policy on the service, and then orchestrate it on each individual backend. So, and this is how the policy enforcement and policies administration is done through this concept of policy administration point, policy decision point, and policy enforcement point. And so we spoke about one network data planes that are policy enforcement point. The policy providers provide service extension, and one network administration points. Basically what it does, it allows customer to provide policy at the larger granularity of this group, for example, of application or workloads, to allow for the orchestration. So let's take a couple examples. How does it work? There's the notion of service drain in Google. Imagine it's 3 o'clock at night and you got paged. What are you gonna do? So you drain first and think second. And that is how Google SREs operate. And so what does drain means? You administratively move traffic around, away from where you got paged or from that service. So what are you gonna drain? You can drain a microservice, you can drain in a zone in the region. The microservice could be VMs, could be containers, could be serverless, set of microservices, and the traffic just moves away administratively. So nothing gets brought down. It's still up, it just no longer receives service. So your mitigation is done because actually traffic moves, so hopefully the other regions are not affected. And you're free to debug whatever happened with the running deployment. And then once you found a problem, you undrain, slowly trickle traffic back, and more and more, and get back to working setup, and wait until next 3 a.m. page happens. And so how does it work with one network? You can see there are different traffic incoming through different data planes, through application load balancer, through service mesh, with gRPC proxyless mesh, or with the Envoy mesh. And they're all going for region 1 now, and then we applied the drain via XDS API, and traffic moved across all of them at the same time, right? And over here, we just showed fully move, but you can imagine moving 10% of traffic, moving 20%, however many percentage of traffic you need to move. Or you can drain right away. Another example is CI/CD Canary releases, where we want to direct traffic to a new version, right? And you can see here there are different clients that are actually humans that go through the application load balancer through some website. There's a call center that is going through internal load balancer point on sale, going through the Envoy sidecar service mesh, and even multi-cloud on-prem going, for example, from the proxyless mesh. And there are two versions of wallet service. There's V1 and V2. And so we provision at the top, and it delivers configuration, and off we go, right? The traffic moved to the V2, sorry. So one network of tomorrow, where we are today, bringing it all together, it's the same picture. We basically done with the central part, and multi-cloud, we have connectivity, and we extended it to the multi-cloud, but we are working on the federation, and we are working on and we have edge, obviously, and we are working on mobile. So it is multi-year investment. The Envoy is one proxy project started in 2017. One Network started in 2020, and our senior level executives committed to a long-term vision. The effort spans more than 12 teams, and we so far delivered 125 individual projects. So majority of Google Cloud Network infrastructure supports One Network, and because it's all open source based, then open source systems are available to be plugged in there. So the question is One Network is right for you? I'd say the most important thing to consider is, do you have executive support or not to do something like that? I wouldn't recommend anybody to do it on their own. Otherwise, the organizational goals need to be also considered. Is the policy is something that your company worries about a lot? Is the compliance is something that is super important? Multi-cloud strategy, developer efficiency that is related to the infrastructure. So that is something I'd say it is important to consider when embarking on such huge project. Plan for long-term vision, but execute on short-term wins. That basically turned out to be a success story because we went without this big outcome. We were just doing one project at a time and improving networking one project at a time, closing that holes in the switches. Yeah, and we didn't talk much about generative AI here. And that's why we decided to ask Gemini to write a poem for One Network and do draw the image. So here it is. It's actually a pretty nice poem, so I like it. Feel free to read it. Yeah, questions?
All right, if you have a question, I can run a mic to you.
Thank you. With all these sidecar containers, Envoy running on all these services, what kind of latency is introduced as a result of adding all these little hops?
Well, they're under microsecond. I mean, when they're local. So it's how network operates. There are no extra introduction. We didn't introduce anything new.
Well, I mean, today there are firewalls, load balancers, but you're also now adding an additional layer of proxy beside each service, right, which doesn't exist today.
No, we didn't. So what we did, we normalized all the load balancers to be Envoy-based, and we normalized all the service meshes to be Envoy-based plus gRPC-based. So whatever people were running, we continued to run. We just normalized what kind of network equipment we are running.
Maybe let me preface with this: for organizations that don't already have or use service mesh, introducing this where before I can communicate with service A to service B is just service A to service B. But now it's service A, proxy, service B.
That's correct. That's considering Envoy proxy. As a sidecar, it introduces latency. That's why proxyless gRPC. It doesn't introduce any latency because it only has a sidecar channel to the control plane. You don't have to change context or anything. But it's under 1 microsecond. I believe so, yeah.
All right, thank you very much, and thank you, Anna.
Thank you.